I'd like to invite here Professor Amparo Galindo from Imperial College London. She is an expert in chemistry, physical chemistry there. She's leading a group with research on statistical mechanical approaches for complex systems, molecular theory suitable for process and solvent design. Her group is at the forefront of the thermodynamic method development SAFT. Some of you may know it. For property prediction. She has also numerous awards. Thank you.
Hello, everyone. Here, if you need as well. Yeah. I think I'm doing like this. Okay. Hello, everyone. Good morning. Thanks for having me today. So, yes, I'm Amparo Galindo from Imperial College, and I'll be telling you about SAFT and CO2 and how we use advanced thermodynamics for carbon capture and efficiency. Okay. So the plan for the talk is I will give you a brief overview of SAFT, trying to give you a little bit of a flavor for what the theory, where the theory really comes from, without too much detail, but to get you hopefully a little bit of understanding. And then specifically move to an approach that we call SAFT Gamma Mi, that we have developed in the last few years, that we are applying for amine modeling, and that we use in the context of high record. And if I have time, I'm hoping to show you a few results when we apply or we integrate SAFT for solvent and process design for CO2 capture. So that's the plan, and I hope I have time to show you all of this. So in terms of the work that we do in Imperial, I work in a group that we call Molecular Systems Engineering. We are a large collaboration that involves 5 academics and a large number of postdocs and PhD students, where we use state-of-the-art molecular approaches to develop techniques and tools to design products and processes. So we start, as you see in the picture, we start with an understanding of molecules. That understanding and tools like SAFT allow us to predict the properties of the systems that we might be interested in. So today, for example, CO2 capture. So we do this property prediction. I show you their isotherms related, for example, to the partial pressure of CO2 for a given solvent. And the aim is to integrate these detailed thermodynamics to really inform process design. And for example, that's again the same process that Sakis was showing to you earlier. So as a group, as I was telling you, we are quite a lot of people there, and we develop tools, or we work in the realm of statistical mechanics, thermodynamics, molecular theories, but also taking it to algorithms and optimization and so on. So some of us are chemists, some are physicists, mathematicians. We are a lot of people working very collaboratively. Okay. So, and then within this large collaboration, my expertise is really the molecular modeling. So that's really my larger contribution to the collaboration. So in terms of the molecular modeling challenge, what is it that we do? So what we address is the fact that we start wanting to understand a reasonably complex system. For example, in the context of CO2, we have molecules like water, carbon dioxide, the amines, which are multifunctional, they can be quite complex, and so on. And we represent them in a molecular way, as you have there. And the plan, as I was telling you, is to deliver predictively the macroscopic properties of the system. So this, for example, is a cut of a ternary phase diagram. In CO2 capture, for example, you need to understand what is ultimately the phase behavior of CO2 with water and the amine, and then all the flue gases that are coming through, and you will have impurities. In high record, we address corrosion and things like this. And so in molecular model, what we do is we propose what we call a molecular model, which strictly is an intermolecular pair potential. These are simple mathematical expressions that describe the interactions between molecules. So, and then the question is, how do we do this? We can write these expressions reasonably simply. You might, anyway, trust me that these equations are simple. The difficulty, however, is that we go from the realm of the molecules, where we can write in simple mathematical forms how 2 molecules interact with each other, but we need to deliver macroscopic properties when we have Avogadro's number 10 to the 23 interactions between molecules. And in the time of machine learning, you would think, well, just, we have mega computers, just, multiply, compute all these interactions between your molecules. The problem is that, you can do a calculation very quickly where you say, if I have to do 10 to the 23 calculations, a simple multiplication to say where is the position of each atom in bulk. And you take the fastest computer you can have, teraflops these days, which compute at 10 to the 12 calculations per second, you will see that to calculate the distances, just the distances between the atoms, let alone the atoms moving and your mixture and all these things, it would take you over the order of 3,000 years. So it's clearly not feasible. Okay, so this is where statistical mechanics comes as an area of science. Okay, this is the machinery that allows us to formally go from the world of the molecules and a formal understanding of the interactions of molecules to deliver macroscopic properties accurately. And some of you, for example, might, I'm sure, have heard of computer simulations, or molecular dynamics simulation, or Monte Carlo simulations. Those give you exact evaluations of the atomic world, but they're still quite computationally intensive, and we cannot integrate those in process design yet, for example. And so the other tools that we have are equations of state. And those of you that are engineers or chemists might have, for example, studied the van der Waals equation of state. Okay, so these are the tools that we are using, the relations in the end between macroscopic properties, but informed formally from a molecular world. And SAFT is one of those. Arguably, is at the moment considered the state-of-the-art equation to do this, okay? So SAFT, I have here just a summary slide. Just sort of to give you the headline, is an equation of a state, so as I said, just a relation of pressure, density, temperature, composition for the thermodynamic properties of complex fluids. And complex fluids are things like polymers, because they are very large, entangled systems. Water is always considered complex fluids because of the formation of the hydrogen bonds that are in the molecule that gives water very special properties. And the amines that we use for CO2 capture are complex molecules because they're multifunctional, they're hydrogen bond, they react, and all these things, okay? And so SAFT is a technique or an equation of a state that allows you to treat mixtures of all these molecules. Okay, so now I have a couple of slides just to tell you where the theory comes from without too much detail, but just to give you an understanding of how is it different to, for example, van der Waals. Why is SAFT, for example, a major step forward in our ability to predict the properties of complex systems, okay? So the theory originally stems from the work of Verdheim in the 1980s, so this is a long time ago now. Verdheim was a mathematician, and he worked on the development of a pair potential, as I say, a mathematical expression that allows us to say how do two molecules interact with each other. He worked to develop a potential specific for associating systems. Molecules, think water, molecules where the interactions of a molecule with another one is not the same, or let's say it's a function of the direction in which two molecules approach each other. Okay, so you're trying to treat ultimately hydrogen bonding. Think of it in that way. Okay, and so he proposed a pair potential. Is this the pointer? It's going to be tricky. Oh. He proposed a pair potential, here U1, 2. So that's the amount of energy binding molecule 1 and molecule 2 as the sum of a single simple spherical potential plus a contribution that accounts for the sticky sites. So here the green spheres are the molecules, and you can see they're just spherical, isotropic, and then we have a sticky site A, B, C, D. Think of them as glue. If two molecules approach each other in the right direction, we can form strong bonds between them. This, hopefully you can see, this would allow you to treat things like hydrogen bonding. This would allow you also, in a limit where the bond between these two sites here is infinitely strong, you would start forming chains of molecules. And then you can go from a theory of associating systems like water to a theory of polymers. And you can make these chains as large as you want, for example, okay? This is a complex problem to solve when you have a bulk of molecules. So I draw for you a few there, but you're trying to answer the question of what is the likelihood that a molecule will find another molecule at a given density, so depending on the number of molecules in the system and so on. So it's a complicated problem. And so ultimately, we need to make approximations, so Verdheim needed to make approximations to solve this, okay? And the key approximation in the theory is that there is only one bond allowed per site, okay? So we don't have what we call multiple bonding. So the fluid that we are representing is the one that you have up here. So a given little site is only allowed to bond to one other, but not to two at the same time, okay? Which double bonding could be of interest in some systems, but that is not accounted for in the theory. In developing these theories based on statistical mechanics, of course, as compared to doing the exact calculations that, as I was saying, however, it would take 3,000 years, of course, we make approximations, and then at some point in the process that I'm going to show you, of course, we have to assess what level of accuracy have we lost in making these approximations, okay? So we have to make sure that the theory represents what we are hoping to represent, and I will show you that in a second, okay? I can pass over this one. So Verdheim was able to, with the approximations of one bond per site, to reformulate the physics of the problem in terms of only two densities, rho 0, the number of molecules that remain not associated to any other molecule, and rho, which is the total density of the system, the number of molecules in the volume, okay? And with that approximation, he was able to show that we can obtain the free energy, the Helmholtz free energy of the system of a complicated, of a complex molecule that is a chain, including association sites, with a reasonably compact expression. Ultimately, all we need to know is what is the structure of the fluid, of the simple fluid before bonding, and what is the free energy of that reference system. Maybe I will not go too much through the technical details. I show for you the equation just to show you that it's surprisingly compact. Of course, this is for a pure compound. When you treat mixtures, the expressions are slightly larger, but they're just summations of components. Okay, and we write SAFT as an equation of a state always in terms of the Helmholtz free energy, A. From the Helmholtz free energy through partial derivatives, you have all the thermodynamic properties, including derivative properties like heat capacities that are, for example, important again in the context of CO2 capture when you're doing your energy calculations. Okay. Okay. So let me tell you, so from Verdheim's theory stems what we call SAFT, the statistical associating fluid theory, okay? And as a summary slide for you of the state of SAFT at the moment, just to tell you that, so the original theory is accurate for the treatment of associating fluids and chains of arbitrary length. This was tested in the original papers. I didn't put the, but these are the papers of the late 80s compared to computer simulations, so detailed calculations that give you the exact solutions. And I'll show you some comparisons in a second. SAFT as an equation of a state was first published by Chapman and co-workers in Cornell in 1990. And then from then on, SAFT is written as an equation of a state for engineering, and from then on it took off. And there's been quite a few reviews. You have a review in the book of Yorgos Kontogiorgis, for example, and I published a review with Claire McCabe 10 years ago already in a book for the Royal Society. And in our group in Imperial, in 2013, we revisited some of the early work we had done and implemented a new potential. I'm going to tell you about that in a second. And that has allowed us to achieve a new level of accuracy that is now relevant for engineering and really for process design. And I'm hoping to reach CO2 capture. And the other advancement that we did was to reframe the theory as a group contribution approach, and I'll tell you what that means in a second. And just for information, it's interesting to know that although this was originally a fluid theory, it can be applied to the solid phase. So that is very interesting and something that is only now starting. Okay, so in short, SAFT is a molecular model theory, so grounded on a firm understanding of how molecules interact with each other and taken to macroscopic properties, the Helmholtz free energy, formally through statistical mechanics. And the molecular model that we are handling in this theory is the one you have drawn there. So it's a model of flexible chains, of tangentially bonded segments, in which we can add associating sites, we call them, the sticky points, okay? So we can add off-center attractive sites to mediate detailed interactions. These are often hydrogen bonding interactions, sometimes they're polar interactions, and they can be reactive interactions, as we do, for example, in CO2, particularly in the reaction of CO2 with the amines. SAFT is a perturbation approach, which relies on the understanding, as I was telling you, formal of simpler fluids initially. So first we have an understanding of a monomer fluid, and from there, the simple potential I showed you of Verdam, and from there we grow the chains. Okay. So before I show you results for real systems, let me just show you, as I was telling you, in 2013 we presented this paper where we reviewed the theory and presented a new level of agreement by incorporating a new potential. So we treat the interaction between two spherical segments, which is the beginning of the theory. Each of these segments forms the chains, so the interactions or the detail of the potential with which these segments interact is critical to the type of agreement that you will have in the end, okay? And we implement what is called a Mi potential. The pair potential is drawn here, and this is the energy of interaction between one sphere and the other one as a function of distance r. So you can see if the two spheres are very far from each other, the energy that they feel from each other is 0. If two spheres are very close, the energy goes to infinity because you have repulsion, and in between, so you have the repulsive range and an attractive range. And we implement a potential that allows us to control what is the shape of the repulsion, how quickly does it come in, or what is the energy related to repulsion as a function of distance, and what is the shape of the attraction, okay? And that's the Mi potential. I won't show you the detail of how that was done, just a comparison to show you the points correspond to computer simulations. So these are now the exact solutions of the total free energy of the system, and the solid lines correspond to the theory. The dashed line was the previous theory. Okay, so you can see there for different, the 24, 12, 18, 9 correspond to the values of lambda repulsive and lambda attractive. So 24 is repulsion, 12 is attraction. The Lennard-Jones potential, for those of you in thermodynamics, is the Lennard-Jones potential is a 12.6, which is up there, actually. So that's Lennard-Jones, okay? And you can see that as you change attraction and repulsion, the properties of the fluid change. This is the temperature versus density. So on the right-hand side, we have the liquid phase. On the left-hand side, we have the gas phase. And the curves tell you when do you have coexistence between the two. That is for a segment. And this is the type of agreement that you can expect for a chain. So we have the monomer down here, a lot of very good agreement. And then the chain increases. So we have 2, 4, 8, and so on. And you can see that as the chain grows, the accuracy is still pretty good, but we are losing accuracy, of course. And this is where you see the approximations that we are making. There is an impact to the approximations, and we can discuss what those are, but it's not so important. Okay. Once we have the theory developed and we confirm good agreement with simulation, we're still in the realm of theory, if you want, then we treat real fluids. How do we do this? So we need to regress using pure component data. In the end, we have a number of parameters to address. We need to decide how many segments form the chain, what is the size of each of these segments, as for example the diameter sigma, and what is the degree of repulsion and attraction. And this is always done by comparison to experimental data. We use typically vapor pressure and saturated liquid density. This is a matter of choice, but in our area, this is usually the way it's done. And again, we can discuss. And we fix a temperature range from 30 to 90% of the critical point. And so what we have to do is we minimize an objective function, which is the sum of errors. And so what we're doing is we minimize the error in the vapor pressure, so vapor pressure experimental minus calculated over vapor pressure experimental, and this is a function of the parameters of the model. So as I was telling you, how long is the chain, how big is each of the segments, what's the amount of energy binding the segments, and then the shape of repulsion and attraction. So you have a computer code, an optimization code that searches through values of these parameters to minimize the error to experiment, okay? The calculations are very fast. This is why, in the first place, we embarked on developing an equation of a state and not computer simulation, and so we can do this on the fly very quickly. Okay. And the result, for example, these are results for CO2, since this is the molecule of interest today. Just to show you, here you have the average absolute deviations in percentage terms, for example, for the vapor pressure of CO2, for pretty much the entire range. The critical point of CO2 is 303 Kelvin, so that's the full range of CO2. And you can see there the error, and we just selected a number of points along the curve, okay? The same for saturated liquid density, and then the densities and heat capacities. You have in graphs here, which are nice to see. For example, this this is the density. These are isobars, so you have 10 megapascals, 20, 30, and so on. And you have here temperature versus density, and you can see the symbols are experiments, and the lines are the calculations, okay? So you can just see that you have very good agreement for the entire thermodynamic space that is investigated. And this is the result of heat capacity, okay? So again, maintaining very good agreement. The heat capacity is of interest for two reasons. One is critical to process, especially when you're doing energy calculations for CO2 capture, for example. And in terms of equations, it's very important because it's a second derivative of free energy, which tells you, so in a way, it's a very strict test of how accurate the theory is. Often we compare only to first derivatives, which is what I'm showing you on the left graph, okay? And the heat capacity, very few equations of a state can deliver this level of agreement. The reason we have this level of agreement is the fact that we are controlling the shape of the pair potential that I showed you earlier. Okay, so that's CO2. We can, in a way, the theory is general. I've shown you only the expressions very briefly for pure compounds, but the theory is entirely general, and we can have any number of components. So we use it, of course, in the context of mixtures. And this, for example, is the phase diagram of CO2 and water. The two fluids are very immiscible, so CO2, you can think of it as insoluble in water, but this solubility remains through the liquid phase as well as the gas phase. So we have a phase diagram that looks like this if we are at fixed temperature. So, 333, so these are your classic temperatures used in the process of CO2. We have on the left a phase rich in water. So this is pressure versus composition, and this is composition of CO2. So the right-hand side is pure CO2, the left-hand side is pure water. And what we have is a phase diagram that mostly corresponds to liquid-liquid separation. Okay, so we have a fluid rich in water with a little bit of CO2, very insoluble, and on the right, a fluid rich in CO2 with very little water. Okay, the processes that we deal with in CO2 capture are on the left-hand side. Okay, so we're on the water-rich side, if you look at the compositions of how much CO2 we have in there. Okay, the theory allows us to describe fully accurately the phase behavior of the mixture, including, as I said, this is not really the region of interest. Well, it's more of interest on the disorder, but really we tend to be on the left-hand side. But the phase diagram, when you look in detail, has a lot of interesting features, and we can describe those in a lot of detail as well. Okay, so from here, with not a lot of time, I'm hoping to show you a little bit on bringing CO2 water with the amines. Okay, these are now reactive mixtures. This is the process that Sakis was showing earlier. We have data profiles for plants operating, for example, and the fact that we have an equation of a state that evaluates the properties very quickly allows us to integrate this equation into the process, okay? The difficulty is, of course, that the amines react with CO2, and that we have a lot of reactions to deal with. And traditional models of CO2 capture, if you find in the literature, rely on kinetic data of all these reactions where we have to treat, in particular, aside from the CO2 water phase behavior, the formation of the carbamates when CO2 reacts with the amine, there's bicarbonate formation, and so on. But there is not a lot of speciation data for solvents beyond MEA. And what we're interested in is looking for better processes, so how can we optimize the process, but also can we find better solvents? And that's a lot of the work that we have been doing in collaboration with the teams in High Record, also in previous collaborations funded by the EU. So what we have with SAFT, through the use of these sticky points that I was showing you, the association sites that allow us to model hydrogen bonding, but allow us also to model reactions, they allow us to model reactions in an effective way. So as I have there, this is a simplified view of chemisorption. So we can model the formation of the bicarbonate pair by associating monoethanol amine with CO2 through using some of the sites. So we add some reactive sites on CO2 that we label alpha 1 and alpha 2, and these specifically are designed specifically to bind to the amine. Okay? This is within the framework of the same theory that I was showing you before. Doing this does not require kinetic data in any way. We characterize the parameters related to the sites based on phase equilibrium data, just like I showed you before for CO2. Okay? So what we do is we assume that these form tightly bound ion pairs, and so we mediate the formation of the pairs thanks to the sites, and the result And then we check that we are delivering the correct phase behavior. In fact, as I told you before, we use a degree of data, of experimental data, to inform what is the size of the sites, what is the energy of these sites binding the reaction. And then we check the level of agreement. This is partial pressure of CO2 with loaded CO2 in the liquid phase. Classic graph in this area at some conditions of temperature. These are results that we did with an early version of the theory. And what we were interested in was confirming that this idea of modeling the chemisorption through the association sites was relevant for these systems. And so here we are looking at, we call these speciation phase diagrams. Here we're looking at the mole fraction versus the loading of CO2, and it's mole fraction of the species that are forming in the reaction. So we have the mole fraction of carbamate in red. These are the key species that lead to the CO2 capture in the liquid phase. Yes, the amine comes through. So red is the formation of carbamate, so this molecule down here, and in blue, the bicarbonate, okay? The points are experimental data, and the lines are calculations. So as you can see, this simplified view of chemisorption, which does not rely on kinetic data, actually works well enough for us to proceed then into solvent design. We're into process and solvent design, okay, in 2 minutes. I'm just going to show you, as we go to solvent design, we need more flexibility to predict the properties of molecules for which we do not have experimental data. So for that, we incorporated an approach that is called a group contribution approach, SAFT gamma mi. And the idea of group contribution approaches is that you can break a molecule into its functional groups, it's pure chemistry, and that then you characterize the various parts of that molecule. Here I have as an example ibuprofen. As I say, you break it into the constituent groups, the CH3s, OH, CH, for example, if you have an aromatic ring. So you have all the spheres in different colors now, and you characterize each of these groups based on data of much simpler molecules. So for example, if you need to characterize a CH3 group here, you use data from an alkane. This is 1, 2, 3, 4, 5, from pentane. There's a lot of data in the literature from pentane. I use that to characterize the blue group. There's a lot of data in the literature for benzene here. I use this to characterize the green group, and then you put it all together. Okay? Why is this useful? This is useful because the data of small molecules, first of all, there's a lot of it, and it's of very good quality. And it's useful because if this idea works, this allows you then to predict the properties of molecules for which you have no data at all. This is very important in pharma. This is why I have ibuprofen here. We do a lot of work for pharma companies, but it's very important in solvent design, in the work that we do and for amine solvent design, where we look for novel solvents that have not been maybe considered yet. Okay? Okay, so this is what we're doing here. So this is the work that, for example, Felipe Perdomo did as part of the Rolling Cup collaboration that we had. So this was a previous grant before the high record work that we have now. You have on the left lots of the molecules he explored. This just represents all the different groups that we have characterized already, and then just to show you that we can deal with very complex phase diagrams where here we have liquid-liquid separation, we have a heteroisotrope, so the top is vapor-liquid and liquid-liquid. And of course, and then we can deal with multi-component systems where we have the amine, water, CO2, large regions of vapor-liquid-liquid separation, which are very important for the process. You need to know where you are in areas where you have stable liquid phase with the CO2 being captured, and where do you have areas of separation, and you need to do something else to separate. Sometimes, I mean, and we've published before, that liquid-liquid separation can be a very good way to capture CO2 and then regenerate your solvent, okay? But that's another talk. Okay, let me jump through this. These are examples of the type of accuracy that we have. And let me very quickly show you that where we want to go is, the last part of the work that we do that I showed you in the first slide is to put all of this in service of molecular and process design. We want to be able to have better processes and to find new solvents. And for this, we develop complex algorithms in which we then integrate the properties of the process as well as the properties of the molecules. Okay? So for example, here we minimize, and the choice of objective function is arbitrary again, but for the sake of economics, we here we're minimizing the total annualized cost of a process like this. We were capturing CO2 from flue gas from this plant. This is in the literature. This was a flue gas stream containing 5% of CO2, to give you an idea, but this is just an example. Okay, so we minimize an objective function subject to some equality and inequality constraints. Some relate to the process, some relates to the molecular models. Okay. We implement the SAFT view of the molecular interactions that I was telling you before without the need for kinetic data. And we are moving in the space of process decision variables. So we're trying to maximize the lean loading, minimize the desorber pressure, and then control the lean solvent temperature. The temperature of the solvent, for example, how much heat we need to regenerate the solvent is a big issue in these processes. Okay? And we move in the space of molecular design. We select a number of groups, and we say choose any molecule that contains these groups. Okay? This is done in a more or less, this is a difficult problem to solve numerically because it contains continuous variables like pressure, like temperature, and discontinuous integer variables like the precise groups that you are using and so on. But I can jump through this. So this was an algorithm developed by 2 PhD students who are now academics in the UK. We can jump through this, and I'll just show you some results. So we consider a reduced molecular space where we can have only up to 2 amine groups, and a larger molecular space with 4 amine groups. And of course, we find different molecules depending on what we are considering. And I just want to show you that if we compare only thermodynamic properties, so I realize this is very fast, but if we compare only solvent properties, let's say we found in the reduced space a molecule called DAP, diaminopropanol. In the larger space, we have a solvent that I'm going to call solvent 3 that contains these groups. Okay? The large space allows for more amine groups. If we look only at the solvent properties, depending on what we consider, one solvent is better than the other. So for example, here, if we look at solvent, how much we capture for a given partial pressure, solvent 3 at low pressure captures the largest amount of CO2. Okay? The CO2 loading is the largest. If we look at the cost of regeneration, for example, MEA, which is in blue, is the best one. Okay? This really is a slide motivating the need to integrate the process and solvent design. It's not easy to choose the best molecule. Okay? We integrate it into the process, and then we find, and I'll go quickly through this, concentrate on the blue part of this, total cost. If we compare the total cost of the process, total annualized cost, which was our objective function, we do 3 separate exercises. First, we say, well, my molecule is MEA, which is the classic CCS process. And what is, if I optimize the process variables, what is the best I can do? And with that, we obtain the blue diamond that we have up there. Okay? And then you say, well, this is before, the blue diamond is before we optimize. If we say I'm going to take MEA and I'm going to optimize process performance, we improve things going to the black line that you have here. So you can reduce the total annualized cost simply by optimizing the process. It makes a lot of sense. However, in red, we compare the case where we say, well, we're going to optimize not only the process, but what is the best molecule that we can have. And we are going to do this at the same time, on the fly. And for this, you are looking at the red scenario. Okay? So simultaneous design of molecules and processes. So this is red here. And again, as I say, just concentrate on the total cost. And you can see that you can have a big reduction in the total annualized cost when you consider both. The bar tells you what is the best case scenario. Okay? On the right-hand side, you have an analysis of why that is the case, where we look at CapEx and OpEx, but maybe there's no need to, I have no time to show you that. No. Okay. So I realize it was a lot of information very quickly, but I hope I've given you an idea of how SAFT can deliver accurate properties of complex mixtures relevant to CO2 capture, and that, importantly for us, that the reactions of chemisorption can be treated implicitly from phase equilibrium data only. We do not need kinetic data, and this allows us to explore solvents, okay? And that moving to a group contribution approach allows us to integrate these approaches to deliver solvent and process design. Okay, with apologies for...